What up, dudes? Here's what we got. We got a mass 1, mass 2, mass 3 hanging all together, connected in some kind of weird thing. And then it's going off a table over a pulley, and this table is made of ice. So the whole point of saying that this table is made of ice is to say that mu equals 0. We good?
Yeah.
All right, here's what I'm going to do is I'm going to get rid of the numbers. I just, you can plug in numbers at the end, and that would be fine. But I'm going to stick with just saying mass 1, mass 2, mass 3. All right. Let's do this. Let's make our coordinate system like this. And here's one of the funky things that happens when you have connected things to a pulley. Pulleys really mess you up in terms of your coordinate system. I'm going to call this the x direction and this the y direction on the tabletop. That's nothing crazy, but what I'm going to do is I'm going to call this the x direction and this the y direction on that, like my coordinate system will change when I'm talking about that object. Why do you think that is?
Because, they're both kind of moving relative to each other, so it makes sense to change it so we can think about the forces that way, because they're all affecting each other.
I kind of think of this pulley as bending my coordinate system. It kind of bends around this way.
Oh, right.
Right, because if you think about it, as this thing moves in the x direction this way, this thing will move in the x direction this way. It would be a little weird to say that if this thing moves in the x direction this thing will move in a y direction that is connected to that x direction over here. Why don't I just make it the same x direction? Does that make sense?
Right.
Okay.
Yeah.
All right, so now what I'm going to do is I'm going to do some of the forces acting on this thing right here. So there's the tension. I'm going to call that T. And there's the weight. I'm going to call that W3. We cool? Do you see any other forces acting on that last object, the third object?
Gravity, but that's the weight.
That's the weight. Gravity is not a force. I think I kicked a few kids in the head because they said gravity. You need to say the weight, right? Because gravity is not a force, it's an acceleration. But anyway, so I've got the weight. I don't see any other forces. So what I'm going to do is I'm going to add up all the forces in the x direction on object 3. So I have a bunch of subscripts here, but really it's just to kind of help me get my information straight. I'm doing some of the forces on object 3 in the x direction, and that's going to equal to the mass of 3 times the acceleration. Oh, cool?
Yeah.
Is this thing accelerating?
Well, we're trying to find the acceleration.
Yeah,
not
exactly.
in the x direction.
It is accelerating because we're trying to find it. All right. In the x direction, at least, it's accelerating. In the y direction, it's not moving anywhere in the y direction. In fact, in this one, the y direction is not moving anywhere. So I'm not going to sum the forces in the y direction on any of these because it's going to be uninteresting.
Gotcha.
The forces in the x direction. All right, so the only force I see is W3. That's going in the positive x direction because that's going down. And minus t is equal to m3 times acceleration in the x direction. We cool?
Yeah.
All right. Now, the tension here is the same as felt by the tension here. So that t is the same. So now what I'm going to do is I'm going to call this, I'm going to do some of the forces on object 2 in the x direction is equal to mass on object 2 times acceleration in the x direction. We cool?
Yeah.
All right. Now, what forces do I see acting on this object right here in the x direction?
2 types of tension.
Why do you see 2 times the tension?
Well, isn't there tension from this, from on the left?
Ah, you're talking about a tension over here.
Yeah.
I have a question. Do you think they're the same tension?
No.
I agree with you. Which one do you think is bigger?
Well, doesn't it depend on which mass is bigger?
No, I would say that 1 is definitely bigger.
Well, the one on the right is bigger then.
Why? I agree with you. I agree completely with you. If you want to say because I think so, because that's just what I think, that's perfectly fine.
Well, it could have to do with the pooling, or maybe the weight of mass 3, but
Well, I'm thinking to myself, this string right here only has to accelerate this object, right?
right.
Whereas this string has to accelerate both this object and this object. So I'm thinking that
okay.
tension on the right is bigger. I'm just saying.
Oh, okay.
All right.
That makes sense.
You know what I'm going to do is I'm going to call this T1 and call this T2 because I don't want to confuse them. And this is also T2, by the way. I don't want to confuse them, but I know that they're different. That's what I know. Are we cool with that?
Yeah.
All right. So
See, this is where I messed up in the problem. I was thinking that they were the same tension.
Ah.
So I kind of ignored mass 2 because, anyways.
Well, Julia, if they were the same tension, then mass 2 wouldn't accelerate at all.
Right.
I mean, if you think about it, if someone's pulling my right arm with 10 pounds and someone's pulling my left arm with 10 pounds, I'm not going anywhere. Right? So they've got to be different. I don't necessarily know if this is hard. I don't want to say it's easy because I don't think it is, but you got to be careful with this.
Right.
All right. So what forces do I see on object number 2? I see T2, and that's positive because it's going to the right, minus T1 equals mass of 2 times acceleration and acceleration. To be honest with you, I'm doing this actually a little slowly. All right, I'm going to do one more sum of the forces. I'm going to do some of the forces in the on 1 in the x direction equals mass of 1 times acceleration in the x direction. We cool?
Yeah.
Can you see this, by the way? I don't know what your camera can see.
Yeah, it's fine.
All right, I'm going to go one line below that. What is the force that is acting on M1?
Just tension 1.
Good. T1 equals M1 times AX. I like that. That's good. Okay. I'm going to take all of this information because here's the question is, what do I not know? I've got 3 equations. 1, 2, 3. Do you see them?
Yeah.
I don't know. I know the weight of object 3, right? I know the tension, or I don't know the tension. I know the mass of object 3. I don't know the acceleration. That's what I'm trying to look for. Okay?
But if you know the tension of, if you know the mass and, well, and then you could probably find the tension based on equation number 3, right?
There we go. See, the point I'm trying to make is, I've got 3 equations. I've got 3 things that I don't know, because I don't know T2, I don't know T1, and I don't know A. If I have 3 independent equations and I have 3 things that I don't know, I can always solve this equation. I can always solve this. It might not be easy to solve, but I can always do it. Here's how you do it. And you already kind of suggested it. I can substitute this T1 into here. That kind of gets rid of all the T1s altogether, right? So let's just do this. Let's take this equation, and I'm going to say T2 is equal to M2AX plus T1, which is M1AX. We cool?
Yeah.
All right. I'm going to factor out that AX because it's the same acceleration. T2 is equal to M2 plus M1 times acceleration in the x direction. We cool?
Yeah.
Oh, hey, there we go. I plug this guy into here. I'm going to rewrite equation number 1, W3 minus T2, but instead of writing a T2, I'm going to write what it is equal to. M2 plus M1 times AX equals M3AX. I ran over that. Sorry. Equals M3AX. We cool?
Yep.
All right. I'm going to kick everything over to the. I'm going to kick this term over here on the right hand side, or on the left hand side, over to the right hand side by adding it. So I've got W3 equals M1 plus M2 plus M3 times acceleration in the x direction. Very cool?
Yeah.
Again, I ran out of room. Darn it. Let's see. W3 equals M1 plus M2 plus M3 times acceleration in the x direction. Alright. Is it alright if I erase this part over here?
Yeah.
I just don't have enough room. Here we go. So, getting A all by itself, I've got AX equals M3 times G divided by M1 plus M2 plus M3. We cool?
Sounds good.
Alright. That's my equation. By the way, I had W3 in the numerator, but I just changed that to M3 times G.
Cool.
The reason why I
See,
did that...
it makes sense. I just wasn't thinking that the tension on object 3 and object 2 were the same.
Or
I
you
wasn't
were thinking it was the same,
Like,
but you weren't thinking that they were different.
right.
They're different.
Yeah. So I need to sort out the tensions. But that makes sense. Thank you.
Alright, my thoughts about this problem. You can kind of think of, I would think of this as one object. I wouldn't even include that T1. Because I can kind of think of this T2 is going to be pulling, it's almost like what I'll do is I'll do sum of the forces on object 1 and 2 in the x direction is equal to mass of 1 plus the mass of 2 times acceleration. Does that make sense?
Yeah.
Because then what is the if I thought of this as one giant object, you know, like if this were a weight of 1 kilogram and this were a weight of 2 kilograms and I put it inside of a box, then it would essentially just be an object that weighs 3 kilograms or has a mass of 3 kilograms, right?
Right.
So essentially that's kind of where I would hang with that. My favorite part of this problem though is the analysis, so let's do that because you know, I mean that's what I always do. What happens if M1 gets really big? Well, first of all, let's check the units, okay? We've got kilograms divided by what is a kilogram plus a kilogram plus a kilogram?
A bigger kilogram?
Exactly. I'm glad you said that. I'm glad you didn't say 3 kilograms. I was expecting you to do that, but the reason why I said it, the reason why it's not a big 3 kilograms is just because I'm talking specifically about units. If I literally were talking about 1 kilogram plus 1 kilogram plus 1 kilogram, then it would be 3 kilograms. But I'm just saying, what are the units of kilograms plus kilograms plus kilograms? It's some bigger number, still kilograms. So I've got a kilogram divided by a kilogram.
So like if M1 or M2 got bigger, then
Yes.
the acceleration would get smaller.
Because the denominator would be getting super huge, right?
Right. And then if mass 3 got larger, then the acceleration would get smaller.
No, actually it wouldn't. Well, it would get smaller. I agree with that.
Okay.
No, wait. If M3 got bigger, what would happen
It would-
to A?
The acceleration would get bigger.
It would get bigger, I agree. Will it just get bigger indefinitely?
No, because it's dependent on the masses of 1 and 2 as well.
That's true. Here's a trick that we use in calculus. And now what I'm trying to do is train your brain to think, you know, for later math, because you're a really smart person. If M3 got really big, one of the things we would kind of say is, I can either think of M3 getting really big, or I can think of M1 and M2 as getting really small, and it would have the same effect, right?
Right.
In fact, I could think of M1 and M2, let's replace those blocks with pieces of paper. In fact, let's take away the pieces of paper and we'll replace that with like a strand of paper. You know, something super light, or feathers or something like that, or a hair off the feather. Then essentially, these ones would be 0, and you would be left with M3 over M3 times gravity. The M3 over M3 cancel out, right?
Right.
And you're left with just gravity, so your acceleration is gravity. Does that make sense?
Yeah, so if you're basically pulling, if M1 and M2 weigh nothing, then it makes sense that the third mass would just fall.
It would just fall. Exactly. Yes, that's great. That's exactly what I'm saying. This thing would just fall if essentially M1 and M2 were 0. I totally agree with that. I love how your thought process is with that. Cool?